All right, so when we are going to go ahead and we are going to start off with our topic. So, all right, so one of when we talk about quantum physics, right? So in quantum physics, we are basically going to be talking about the nature of light, and also we're going to be talking about the nature of electrons. Now, before we can actually start talking about the nature of light, because I know you have gone over the topic yourself as well. So we have this question that's been going around, and that is the dual nature of light. Is light acting like a particle? Is light acting like a wave? And what uh, experiments have been done, or what theories are there that actually support, or what theories do we have that actually show the dual nature of light? Now, so before we talk about anything else, right, we have to talk about something that is known as Huygens principle. What is Huygens principle? So Huygens was this scientist. Huygens was a scientist who was, of course, studying about the wave particle duality. Okay, so the dual nature of wave and particles. He basically came up with a principle. That principle was to predict the future movement of waves if we know the current position of a wave front. So if I know the current position of a wave front, right? If I know the if I know the current nature of a wave front, I can predict the future movement of the waves. Now, how does that work? How can we predict how a wave would move in the future, right? So, the basic idea that he came up with was this. Let's say this is the current wavefront that we have. This is my current wavefront. Now, on this current wavefront, basically what he said was that we will consider each and every point on this wavefront to be a new source of circular waves, right? So he said, each and every point on this wavefront, each and every point on this wavefront, we will consider each and every point to be a new source of, or a source of new circular waves. So I will have circular waves coming from this point. I will have circular waves coming from this point. Each point on this wavefront is going to be a new source for circular waves, right? So this is basically what Huygens suggested, that each and every point on a wavefront is going to be a source for a new circular wave, right? Now, what is going to happen that when the small waves, right? The small waves that have been made, so if we join all of the small circular waves that have been made, if we join all of the small circular waves that have been made, we can predict the new wavefront. That this is where the new wavefront is going to be located, right? So that's what Huygens said. He said that if I have a wavefront, so every single source or every single point on that wave is a source for a new wave. It is a source for a new wave. The new wave will be circular waves that are all going to be moving away from those small points. And if we plot this on a diagram, if we make a diagram, so basically he called this is your primary wavefront. From the primary wavefront, you can see that all of the points in the wavefronts are acting like a source for smaller circular waves. He called these smaller circular waves, he called them secondary wavelets. And then if we plot the position of these wavelets, if we join the position of these wavelets, what will we see? We are going to see that we will end up with a new secondary wavefront. Right? And if we consider, right, the your Huygens principle, so we can understand all of the wave um, all of the wave features that we have seen. For example, what was the feature that you and I had studied? We had studied interference. We had studied superposition. So this is superposition, right? The waves are superposing on top of each other and giving you a resultant wave that will be our new wavefront, right? So waves can undergo superposition. They can undergo diffraction, right? All of these principles can be used for all of this can be explained by using Huygens principle. For example, what was diffraction? Diffraction was if I have, for example, a gap and I was passing a wave through that gap. So this is my wave and this is my gap. So as the wave is going to pass through the gap, it is going to diffract. It is going to bend, right? You and I had seen that when they're going to bend, they're going to end up looking like this. Now, if we consider Huygens principle, it will make sense. How does it make sense? If this is my wave front, right, that is passing through the gap. This is the wave front that is passing through the gap. So on this wave front, each and every point is going to be a source for a new wave, right? Each and every source is going to be a source for a new wave. So each and every point is going to generate its, or each and every point is going to lead to the production of its own circular waves, right? And we can use this concept to predict how exactly is it going to diffract. We can use this concept to predict how is diffraction going to take place? How is superposition going to take place? How is interference going to take place? Right? All of this can be predicted by using Huygens principle. So Huygens principle, quite frankly put, you don't need to know much more detail other than this, that Huygens principle can be used to predict the movement. No, I gave you the example of diffraction. We can use it to predict the movement in reflection, in refraction, in interference, right? In all of these features, we can figure out exactly how the light wave is going to move simply because of the fact, if you follow Huygens principle, which simply state that each point on a wave front is going to be a source for a new circular wave. And if we plot it, if we plot it on a graph or we plot it in a paper and consider superposition, so we can actually predict where the new wavefront will be and exactly how the wave is going to move. So that is what Huygens principle actually is. That is basically all there is to Huygens principle. Now, so when we are talking about it, the entire question that we have to understand is that whether light is in the form of a wave or whether the light is in the form of a particle. Okay. Now, when we talk about light in the form of a particle, hold on, give me 1 second. Let me show this to you. If we talk about light in the form of a particle, right? I have a really nice table actually that will make it much easier. So we have, over the years, we have numerous evidence that actually supports light acting as a wave. What are the evidence? Everything that you and I have studied, everything that you and I have gone over, the properties of waves, right? They all of them actually all of them actually support the fact, or all of them actually support the logic that all of them support the logic that light travels as a wave, because light undergoes diffraction, light undergoes interference, light undergoes um, superposition, right? All of these are features that we see with waves. So we have got quite a lot of evidence that light actually travels as wave. We've got a lot of evidence that light travels in the form of waves. Now, so why was there a question in the first place? Why was there a question? Why were they even wondering about how wave actually travels? Right? So the reason they actually started to wonder about why wave travels, or is wave a particle, is because of an experiment. Okay. The experiment is known as the photoelectric experiment. The photoelectric experiment worked like this. That the scientists, what they did was that they actually had a plate of zinc. So this plate of zinc had a negative charge on top of it. Okay. Now, this negatively charged zinc plate was connected to it. So they had this box, okay, this metal box. And inside the metal box, the zinc plate sort of extended or connected to the inside. Then on the inside of the plate, they had a gold leaf, right? Like a very, very, very thin foil of gold metal. Now, the concept was this, that over here I have my zinc plate. This zinc plate is negatively charged. By the principle of your induction, right? Because what is going to happen that if I have a particle that is negatively charged and I bring an uncharged particle on, and close to it, what will happen? A charge will be induced, right? And this is something you might have studied in your IGCSE, right? If I have a sphere that has a negative charge on it, and I bring close to it a metal sphere that has no charge, what is going to happen? That the negative electrons will be repelled away from the sphere, right? They will move towards the other side of the sphere. They will move away from the sphere that has a negative charge on it. And as a result, what's going to happen? One side of the sphere will end up with a negative charge, and one side of the sphere ends up with a positive charge, right? This is what we had studied in IGCSE. So what is going to happen? Similarly, if my plate has a negative charge on it, right? What's going to happen that when I'm going to place a gold leaf on it, that gold leaf is going to end up developing a positive charge due to not electromagnetic induction, I should say, due to the induction of charge, right? Due to the induction of charge, charge is going to be induced on the gold leaf, and as a result, the gold leaf will become positive. So the positive side of the gold leaf and the negative zinc plate will attract each other. So the gold leaf will be attached towards the top. It will be attached towards the zinc plate, because remember the zinc plate was connected to the inside. So it will be connected to the top of the metal box where the zinc plate is connected. This is how the normal setup was. Now, what the scientists discovered was that if they did the experiment with ultraviolet light, but technically speaking, theoretically, it can be done with the entire electromagnetic spectrum, but the experiment was done with ultraviolet light. So they shone ultraviolet light on the zinc plate, the one with the negative charge. What the scientist observed was that the gold leaf would fall down to the bottom of the box. Now, why was the gold leaf falling down? Why was the gold leaf first held in place? Why was it even held in place? Due to the fact that the zinc plate had a negative charge. The negative zinc plate was holding the gold leaf in position. So if the gold leaf is falling down, what does that mean? That means that the zinc plate must be losing its negative charge, right? So the scientists started to wonder, why exactly is the zinc plate losing negative charge? What is happening that is causing the zinc plate to lose negative charge and for the gold leaf to fall to the bottom of the box? So they started to run further experiments and started to further study it. Now, what they ended up figuring out was that what was actually happening is this: light is made up of small packets of energy, right? They're made up of small packets of energy. Those packets of energy are what we call photons, right? Those small packets of energy, the small quantum packets, the small quantum packets of energy, that is what they call photons. Now, what they noticed was that when these packets of energy, when these photons would fall on the negatively charged zinc plate, what they would do is that they would make that zinc plate lose electrons. It would make the zinc plate lose electrons. How? The way it works like this is, let's say that I have my electrons. Now, you have not gone over chemistry, but if you have done chemistry in IGCSE, this will still make a bit of sense. When we talk about the structure of an atom, what is the structure of an atom? We have a nucleus in the center, and that nucleus is surrounded by what? Shells. And what do we have in the shells? Electrons. In IGCSE chemistry, you might have studied that we have, shell number one, shell number two, shell number three. To make your concept now regarding this um, shell a lot more clearer, is that these shells are not something tangible, right? It's not something you can actually observe, these shells. If you talk about the solar system, so in the solar system, if you look at a diagram, you can see the orbits of the planets. But if you will take a look at an actual image of the solar system, the orbits are not something that are visible. The orbital lines are not visible, right? All you can see is a planet orbiting the sun around a certain track, right? Around a certain pathway. Similarly, what are these shells? These shells are energy levels. So those electrons that possess the least amount of energy, they will be in the lower shells. They will be closer to the nucleus because they do not have that much energy inside of them to move away or to be further away from the nucleus. Those that have the highest amount of energies, those electrons will be found on the outermost shell, the shell that's furthest away from the nucleus, because that is the highest energy level in that atom. So, yes, Ashwish?
Why does it have the highest energy level?
The energy level possessed by each electron is going to depend upon properties of that atom. So different atoms are going to have different properties. They have different, if you talk about the nucleus, they have different number of protons, different number of neutrons. So it's all going to depend upon the atom itself, right? So when we talk about electrons, electrons do possess their own energy, right? They do possess their own energy level. And so, based on their energy level, they can occupy a certain shell, right? So, that is simply based on I could go into more detail, but then that's going to be a bit too much chemistry itself. Basically, when we talk about an atom is balanced by three different factors, right? It's balanced by the nuclear attraction or the charge of the nucleus or how strong a nucleus is. It's affected by the repulsion between the electrons. It is affected by the, it is going to be affected by the it is going to be affected by the number of neutrons number of shells that are present in total. So based on these three factors, and they have to balance each other out, that is what leads to an atom having a certain structure, right? So the based on how much energy an electron has, it is going to be able to occupy a certain energy level only, right? Now, what happens that, so the shells, what are shells? These shells are all energy levels, okay? Now, the interesting thing is that it's not necessary that a shell or an electron on the innermost shell or the lowest energy level will stay in the low energy level. It's not necessary. That electron can go from a low energy level to a higher energy level. How? Right? For an electron to go from a low energy level to a higher energy level, we need to provide it with some kind of energy. That energy needs to come from somewhere, because energy cannot be created nor destroyed, right? So the energy needs to come from somewhere. Where is the energy coming from? Photons. The photons, what are photons? Quantum packets of energy. They are basically your quantized energy that has been put into really small packets, right? So these photons are small packets of energy. When these photons fall onto the zinc plate, they can cause these electrons to become excited by providing energy. So the photons will transfer their energy to these electrons, exciting the electrons. And as the electrons are going to be excited, they are going to they are going to uh, leave the atom. Yes, Ashwish?
So you're saying the closer the electron is to the nucleus,
Yes.
the less the
Yes.
less energy it has.
The less energy it has. Yes, correct.
So
Correct.
if it's closer to the surface, it requires less energy to be
Yes.
excited and
Yes.
become
And
a
outer
photon.
yeah, basically, yes. So, and the outermost electron, if I want to remove the outermost electron, I do not need to input that much energy. If I want to remove an electron from the innermost shell, that will require considerably much higher amount of energy.
So it would
So,
have need a
yeah, yeah.
less work function for it to be removed.
Yes, yes,
And it's
yes, that
closer
is,
to the surface.
yes, that is
So
correct.
then there's
Because
more
if it's,
energy for kinetic energy.
yes, exactly. That is correct. That is correct. So the electrons, right? So what's going to happen that a photon can transfer its energy to the electron, allowing the electron to even leave the atom itself, right? The electron can actually become delocalized. And so the electron can actually end up becoming delocalized. It can provide enough energy where the electron can become delocalized. It can escape the atom. And what is going to happen that the loss of electrons from the atom is going to lead loss of the negative charge. The loss of the negative charge is going to cause the gold leaf to fall down. So this is what they discovered, that these electrons, this is what they discovered, that whenever they would um shoot ultraviolet light on the negatively charged zinc plate, the gold leaf would fall down. Why? It would fall down due to the fact that the light was causing the electrons to gain energy, causing them to become excited. So the electrons were released, or the electrons were produced, and that would lead to the loss of the negative charge plate. And these electrons that were being released, these electrons were what they called as photoelectrons. Now, they decided, now this was not proof at this point, right? They were still not certain that light is working as a particle. I will show you evidence for that. They were still not sure that light was working as a particle, okay? So they repeated this experiment many different times with different intensities of light, with different frequencies, different wavelengths. This experiment was repeated multiple times. And each time the observation noted or the observation was uh, written down, right? Now, there were certain discoveries that they made that actually supported that light is working as a photon. Before I go over those discoveries with you, we need to first talk about what is actually happening in the experiment itself. Now, they made two important discoveries. One important discovery that they made was that there is a minimum amount of energy that needs to be supplied. These photons, they need to have a minimum amount of energy. If they do not meet that minimum amount of energy, if they do not have that least required amount of energy, there will be no loss of electrons. The electrons will not be excited, right? The electrons will not be excited. They will not be able to leave the surface of the metal plate. So they need a certain minimum amount of energy. That certain minimum amount of energy that they require is what they called as work function, which was denoted by a Greek symbol of psi. So there is a minimum energy required. Yes, Ashwish?
So then what's the threshold frequency?
I'm going over it. I'm going over it. So they
Okay.
required a minimum amount of energy. That minimum amount of energy was what they determined as work function. Now, for when you're talking, for now, remember how I told you that they repeated the experiment at different intensities of light, different frequencies of light. So what they discovered was, now what they discovered was, and in fact this will make a bit more sense. Let me open up a table for you, 1 second. I don't think I have it. Yeah, it's here. Okay, so this was the discoveries that they made, and this discovery will make everything so much more clearer to you. This is actually not in your book. This is a separate table that I have that I feel like makes things very interesting. Okay. So before we talk about what threshold frequency is, let's first talk about what are the observations that they made. Okay. So one of the observations that they made is that the emissions of electrons happened as soon as the light shines on the metal. So the moment they would switch on the ultraviolet light, the gold leaf would fall down, right? Now, if what the wave model, right? The wave model suggests, if we look at the theories of waves, that it is the intensity of the light that should be important over here. If I use very weak light, then the response might not be immediate because intensity is equals to power per unit area. So if my light is very intense, then yes, it should be producing an immediate effect because it has a lot of power. But if I use a really weak light, really low intensity, there should be some difference observed, right? We should see some difference between a weak light and a really intense light. But they saw it didn't matter what was the intensity of light they were using. It did not matter. Even one single photon was enough to release an electron. That's what they observed. So that was an observation that they made that could not be explained by the wave model. They could not explain this observation by the wave model. So this was one of the observations that suggested to them that yes, this must be a particle model. There must be some kind of particle. That is why even if one particle is there, we will see loss of electrons. Because if light was a wave, then intensity should have been an important factor. We should have seen a difference between low intensity and high intensity. And that was their second observation as well, because they repeated experiments at low and high intensity. They noticed that when they used low intensity light, yes, Ashwish? Yes, Ashwish, you want to say something?
So you're saying for the first point that it
Mm-hmm.
should happen instantaneously.
It happened. Yeah, it was their observation. It's not that it should happen. That is how it happened. That is what they observed. This is their observation. So when they did the experiment, this is what actually happened, that it would fall down, the gold leaf would fall down instantly, which to them didn't make any, which, if you think of light as a wave, it doesn't make any sense. To see such an immediate response, the light has to be a very intense light, because intensity is power per unit area. So even if I use that's their second observation, right? Even low intensity light was very effective, which doesn't make any sense if you think of light as a wave. If light is a wave, then low intensity light should not produce such a good response as high intensity light, right? If light is a wave, then low intensity means low power. So, would you get as good of a response as you would get with high intensity? No, right? There should be a difference. You should, if light is traveling as a wave, then between, yes, Ashwish?
So you're saying that if they thought if it was a wave, that means
Mm-hmm.
they would need a very intense light with high enough
Yes,
power to take the
yes,
electron away. Then when they
yes.
use low intensity light, the same effect still happen.
Yes, exactly. So that's what they observed, that even when they were using low intensity light, the same effect would happen. The gold leaf would fall down instantly. So intensity seemed to have no effect on the loss of electrons or the emission of electrons. That's what they observed. This is what made them think that light is not working as a wave. This is why they started thinking of light as a particle, because a wave, intensity is important for a wave, right? So they said if light is a wave, we should see some sort of difference between low intensity and high intensity. But when they actually ran the experiment, they found out that it didn't matter what was the intensity they used. The emission of the electrons would happen instantly, even at low intensity, even at high intensity. Even low intensity light was just as effective as high intensity light, right? This is what they actually ended up observing, right? Then, so that, what
Yeah.
did that
So then
suggest
how
to them?
does intensity of the light relate to the number of photons?
The intensity of the light, when we are going to talk about it, so the greater the intensity of the light, right, more power per unit area, the stronger your light is going to be, the obviously the stronger the light, the greater the number of photons that are going to be present, because when we are going to talk about it, intensity is a right power per unit area. That power is, what is power? Power is energy per unit time, right? So what would happen, that the actual energy, let's say that the total power, a high intensity light, for a high intensity light, the total power would be higher, right? Now, each photon will have the same amount of energy. That will not change. Each photon is going to have the same amount of energy regardless of how strong my light is. The amount of energy in photon is going to be the same. So, a light with less power or less intensity, the photons, the energy of the photons is the same. Between low intensity and high intensity, the energy of the photons is the same,
So you're
right?
talking about
So,
the total energy.
yes,
So if there's more photons,
exactly.
so more total energy.
Exactly.
Okay.
Exactly. If you wanted to have a higher power, you can't change the energy possessed by the photon itself. So what will be greater? The number of photons. So photon model, when they talked about the photon model, they said that the reason we are not seeing any effect due to intensity is because light is not working as a wave. Because if it was working as a wave, we should have seen something. It's because light is working as a particle. So low intensity simply means that we are seeing less photons, but the energy of each photon is the same, right? That's what they said. They said we can explain this if we think of light as a particle. Simple. Then another thing they noticed is that increasing intensity of light increases the rate at which electrons leave the metal. So what would happen that if they increase the intensity of light, right, it would increase the rate at which the electrons would leave the metal. So if you increase the intensity, the electrons would leave faster, which makes sense. Why does it make sense? Because if we follow the photon model, that means that there will be greater number of photons being produced per second, because low and high intensity means greater number of photons. So there will be greater number of photons per second. As a result, more electrons will be released per second, right? That is what they actually ended up observing. They said, okay, when we increase the intensity of light, it makes no difference to the emission of electrons. The emission of electrons happens regardless of the intensity of light, but it does seem to have an effect on the speed at which the electrons are being released. So that was another observation that helped them conclude that intensity is related to number of photons. So higher intensity means more photons per unit second. So more electrons will be released per unit seconds. So this was another observation that helped them conclude that the intensity does not have an effect on the energy of the photon. Intensity has an effect on the number of photons. Then they also noticed that increasing intensity has no effect on the actual energy of the electron. So the electrons, when they were leaving the surface of the metal, they would possess a certain amount of energy. That certain amount of energy that they would possess, right? That certain amount of energy, they saw that it did not change regardless of whether they used low intensity light or high intensity light. The electrons produced all seem to have same energy regardless of the intensity itself, which again supported their theory that intensity is linked to the number of photons and not to the energy of the photons, right? So this was another observation that supported them, that the intensity is related to the energy of the photons, sorry, the number of photons and not the energy itself, right? And all of these three observations were what refuted the wave model. This was the one that allowed them to deny the wave model, or to say that the wave model cannot explain these observations. Because if we think of light as a wave, then intensity should have an effect on the energy, because intensity is power per unit time. So these were the three observations they made related to intensity. So intensity refuted the wave model. Then they said, okay, fine. So the energy of the photons does not seem to be related to intensity. Intensity only seems to be linked to the number of electrons. Okay, sorry, number of photons. Well and good. Now, their question was then, okay, fine. What actually affects the energy of the electrons? What actually affects the energy of the photons? Because clearly the intensity of light does not work. So they said, let's start experimenting with frequency of light. And that is where frequency comes into play, and that is where threshold frequency comes into play. They discovered that the frequency of light is what is linked to the energy of the photon. If they change the frequency, they would change the energy of the electron. Higher frequency meant that the photons would actually have a higher energy level. And so what they did was that we know that what is work function? Work function is the minimum amount of energy required for an electron to escape an atom, or for an electron to be for an atom to escape. Sorry, I'm saying atom, electron to escape.
Is it different
So
for each material?
yes, the value is different for each material. Exactly. So they said that, so there is a minimum amount of energy that is required. Energy is dependent on frequency. So if there's a minimum amount of frequency, then there must be a minimum value for, minimum amount of energy, then there must be a minimum value for frequency as well, because energy of a photon depends upon frequency. So if if there is a minimum requirement for energy to allow the release of electrons, then there must be a minimum requirement of frequency. That minimum required frequency to call emission of an electron is threshold frequency. So threshold frequency and work function are almost the same thing. Not almost the same thing, but they're both on the same concept. Your work function is the minimum amount of energy required for emission of an electron. Threshold frequency is the minimum frequency of light, right? Or the minimum frequency of our electromagnetic wave that would cause the release of an electron. So threshold frequency is the smallest frequency we require, and work function is the minimum energy required for
So
the emission of
let's say you
electron.
have
Yeah.
threshold frequency is like
Yes.
10, and if the frequency is applied to the whatever is like if the photon frequency is like
Mm-hmm.
20, which is greater than the threshold
Yeah.
frequency, that means
Yes.
it has a higher energy, and then that means
Yes.
like
Yes.
depending on the work function, it could have
Yes.
maybe more kinetic energy.
Yes, exactly. That is correct. That is completely correct. So basically, that was actually the second observation that they made. That if they increase the frequency of light, it would increase the maximum kinetic energy of the electrons. So what would happen is that increasing frequency of light. So what would happen is that electrons require a minimum amount of energy to be emitted. If my electrons, so the energy I am supplying is greater than the work function, the energy I am supplying is much, much greater than the work function. So from my energy, if let's say you said we are providing an energy of 20 joules, from that 10 joules is my work function. So 10 joules I need for the electron to be emitted. But once the electron has been emitted, there is another 10 joules of energy left behind. That 10 joules of energy will turn into kinetic energy of the electrons. So at threshold frequency, the electrons will have no kinetic energy. Keep that in mind. At threshold frequency, the electrons will have no kinetic energy. Why? Because threshold frequency is the minimum frequency required for emission of an electron. So threshold frequency is equals to work function. So at threshold frequency, we are just giving the bare minimum energy for the electrons to escape. We're not giving the excess energy for them to also gain kinetic energy. Then, if I increase the frequency of light, if I go past the threshold frequency, then a certain amount of the energy that is equal to the work function will be utilized in causing the emission of the electron. And once the electron has been released, the rest of the energy that was not utilized, the rest of the energy will turn into kinetic energy of the electrons. So the electrons will move faster. So this was another observation that they made. And both of these observations, they could not explain using the wave model. Because the wave model suggests that if we talk about waves, so in a wave, what is going to happen? In a wave, what is going to happen? That frequency is, what is frequency? Frequency is the number of oscillations per unit second, right? So they said it is simply oscillating faster. So if we think of light as a wave, then the energy of the particle should not be affected. The only thing that should be affected is the release of electrons. So the rate of release of electrons. So they said if light is traveling as a wave, then the frequency should only affect the speed of the release of electrons, how quickly the electrons are being released. It should not have an effect on the energy, right? So these two observations, they could not explain using wave model, but both of these can be explained if we consider light to be traveling as a photon. So keeping this in mind, they came up with a photoelectric equation. What is the photoelectric equation? So we have, when we talk about energy of light, okay, or when we talk about energy of a photon, energy of a photon can be determined by using a formula that is energy is equals to hf. The E stands for energy in joules. The H, what does the H stand for? The H is a constant specifically known as Planck's constant, right? Specifically, we call it our Planck's constant. And F, of course, is going to stand for our frequency. So the value of H, by the way, the value of Planck's constant is 6.63 into 10 raised to the power of negative 34. This will, of course, be given to you in your data sheet, so you don't have to worry about it. Into 10 raised to the power of negative 24. No, it's 34, I think. Yeah, it's 34. Yes, definitely.
Yes, 34.
Yeah, 34 joules second, right? So this is the value for Planck's constant. So they basically said that E is equals to HF. This is the formula that we can use to calculate the energy of one single photon. And what is a photon? A photon is, quite simply put, a quantized packet of energy. So
What does
when
quantized?
quantized simply means that the minimum smallest amount by which a quantity can change. That's what it is. The smallest, like, numerical value that we can have by which any quantity can change. That in physics we have determined that value to be we have developed that cause that to be quantum. That's what quantum means. The minimum smallest possible value by which any quantity at all can undergo change. That is what we call as that's what we mean by quantum. Okay. And so basically, if we talk about quantum physics, right, in quantum physics we do not believe in infinite changes. We don't believe that because technically if you and I talk about it, you can say Miss Small can be 10 raised to the power of negative 20, negative 30, negative 40, negative 50, negative 60, negative 70. We don't know how small anything can be, right? So, but in quantum physics, what the scientists believe is that they do not believe that the change can be infinite. They do not believe that my energy can change by an infinite value. They say that no, there has to be a minimum smallest value. So, for example, energy of a photon, there's a minimum small value. The energy of photon will not change below the minimum value. Right? That's what the current theory stands. So for that, they use the term quantum. The smallest possible value by which any quantity can change is known as quantum. And so it is sort of, yeah, that is basically what it is. So they are basically quantized. Quantized simply means that they are extremely small. That's it's a simply way of saying they're extremely small. So photons are quantized packets of energy. Okay, now what is going to happen? So this was the equation that they came up with. Now the minimum energy when we talk about it. So the energy that my energy, by the way, this is depends upon frequency. You can see that, right? Energy depends upon what frequency is equals to HF. So energy depends upon frequency. So whatever is the total energy supplied by my wave, right? That is going to be equal to work function because I have to cause emission of the electrons. And it also has to be a sum of work function plus kinetic energy. So whatever is the that's what I told you, that the energy that is being supplied to an electron, that energy is going to be utilized in causing the emission of the electron. And once the electron has been emitted, whatever energy is left behind is going to be converted into kinetic energy of the electrons. Yes, Ashwish?
So you know how like
Yeah.
the further up like the closer the electron is to the surface of the material,
Yes.
the less like the work function decreases, right?
Yeah, yeah.
Then that mean that the threshold frequency changes?
Threshold frequency does depend upon work function, yes. If a particular material, so when you talk about work function is sort of a value that we generally talk about based on material to material. So every material tends to have its own value of work function. Every metal basically tends to have its own value of work function, right? When we talk about loss of electrons, so generally loss of electrons happens from the surface of the atom. It happens from the outermost shell. We do not generally see loss of electrons from the inner shells, because that would require a huge amount of energy. So whatever is the least amount of energy, so obviously the least amount of energy is going to be if I am removing an electron from the outer shell, right? So whatever the least amount of energy is to cause an emission of electron, that electron can be anywhere, but the least amount of energy that will cause an electron to be released, that is basically what your work function. So generally, work function is a term that we use for outermost electrons, because if we talk about innermost electron, if I want to remove an inner electron, then that will require an energy level that's going to be much higher than the minimum required energy. So that's technically not considered as work function. For work function, we're generally talking about the outermost electron, because the work function is the least required energy. So least required energy has to be from the outermost electron. Okay, so total energy
Yeah,
that we're
makes
supplying, good. Okay, so total energy that we're supplying is going to be equal to your work function plus whatever will be left behind will be converted into kinetic energy of the particle. So that gives us our equation that HF is equals to work function plus half mv squared. Also, when we're going to talk about work function, so work function is equals to h f naught, where f naught stands for threshold frequency, where the f naught stands for threshold frequency. Okay, so why? Because if I am at the minimum threshold frequency, I only have enough energy to cause the electron to be emitted, right? Because I'm only providing the minimum frequency or the minimum energy for the electron to be emitted. So there will be no kinetic energy in that situation. If I am at threshold frequency, then my particles will have no kinetic energy because I only have enough energy for work function. So my work function is equals to h f naught, where the f naught stands for threshold frequency. So if you are ever in a situation where you have been provided with threshold frequency, you can calculate the work function simply by using h f naught, and that would provide you with the minimum energy required for emission of an electron. That would be your work function. And this is basically the equation that we have for our photoelectric effect. Right. So this is all clear, right? No confusion about what we have discussed so far.
yeah, makes sense. Thank you.
Okay. Okay, Ashwish, so, we'll go ahead and stop it over here for today. And inshallah, we'll continue with the questions in the, sorry, the topic in the next class. All right.
Yeah, thank you, miss. Have a good day.
Thank you. Thank you, Ashwish. Have a good day.